Hello everyone, welcome back to yet another video of the day. Let us solve today's lead codes daily challenge. The problem is house robber. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. So what does that mean? Each house has a certain amount of money stashed, and the only constraint stopping you from robbing is each of them is that adjacent houses have security systems connected. Okay, the two adjacent houses, if it is broken, then the police will contact automatically. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Great. I hope this is similar to some sort of problem that we solved previous day or a day before. So let us take this 1, 2, 3 and 1. So let us consider I am robbing this first house. Then I will be having a sum 1 till now. If I have robbed this particular house, then I cannot definitely rob this house, because since it is adjacent, if I rob this both the houses, then the police will come and catch the robber. So I cannot rob this particular house. So I will be robbing this house. That is, if I'm taking this one, I cannot take this two, so I will be moving. If I'm at this position I, and I have picked I, if I have picked I, then move sorry then move to I plus 2, because I cannot pick I plus 1. Consider I have not picked this I. That what does that mean is, if I'm not picking this I, then I can move to I plus 1 and I try to pick this element 2, because I can rob this house too. Because since I have not picked this one, I can obviously pick this one, because it is not adjacent connected, which where I am picking both the adjacent houses. So I can definitely pick this I plus 1. So if I have not picked I, then move to I plus 1. So this is the one thing that we can do. So it is quite similar, right? So what we can do is, for the optimal answer for this solution is rob house 1. If I'm robbing this house 1, then I can move to 3 and rob that 3, and I can make a total sum of 4. That is our optimal answer that we can get. If I'm robbing 2, then I can obviously leave out this 1 and 3. I can rob this 1 only, so I will ultimately get a total sum of 3 only. So in this example 2, we can rob the house 1, then I can move to the 2 positions and I can rob the house 3, which the sum money 9, and again I can move to the 5th position, where I can rob the house 5 with money 1, and the total sum will be 12. But I cannot rob this 2 and 7 because it is adjacent in one go. So that is the problem. It is quite similar to pick and not pick, and since we want to take all possible cases, if we are taking all possible cases itself, it is going to be some recursion. So we can try to do recursion on this problem, and we will try out all possible ways, and our recurrence relation will be something like this. If I'm picking like this, then I can take the nums of I and I can move to the next question, solve of I plus 2. And if I'm not picking this case, then I can directly move and go and do the other possible ways to find the robbed money, and I will go to I plus 1. So what is our states determine? The dp of I determines, I'm going to have dp of I determines the total, the maximum amount of money I can rob till I, from 0 to I, from 0 to I, without alerting the police. So this is the states that we can define. So we can easily determine this. So we can try to do the recursion, and then we can try to memorize that solution, and we also can try out the most optimal solution by space optimization. Before that, we can do this recursion. The time complexity will be exponential, and for each step we are exploring two possible cases, so it will take 2 power n. So we can take the size of this nums array. Then what we can do is, just a minute. So we can actually take the size of the array. Then what we can do is, we can write a function that is going to return max money rob. This is going to be my function, and I'm going to pass this nums, and I'm going to start from the index 0, and I'm also passing the n as well. So now let us try to do a recursive function. This is going to return me a max money robbed of integer value, and it takes the parameters nums and int and size n. And then what we can do is, we can have a base condition. What is the base condition? Is nothing but, if my I have reached the n, then what we can do is, we can return 0, because that is our maximum limit that we can go in our num. So we can just return 0, and there will be two options: either pick this current house, or else we can say it as rob per house. And we can have another option that is not robbed, or we can say it as robbed and not robbed. So this is a robbed house. If I robbed this house, then I can take the current value nums of I, and I can go to the next recursive call max money robbed, where nums is passed, and I will be moved to two positions and the size n. And if I say it as not robbed, then I'm not picking this current cell, so I will not be adding to that value to my answer. So I will be calling the max money robbed function with nums, and I will be moving to the next position because it is not going to be adjacent. So I can move to the next position to maximize our answer, and finally I can return the maximum of this both robbed and not robbed. So this is our recursive function, and this should get accepted. So now let us try to memorize the solution. Yeah, it gets accepted. So what are the parameters changing? We want to have a dimensions according to their parameters, the number of parameters. So depending on the number of parameters, so the number of parameters that changes in this recursive function is only one. So we can have a vector of int dp. So the depending parameters is one, so we can have vector of int dp of size n, and it is more than enough, I guess. Yeah, and we can initialize everything to be -1, and we can pass this dp here as well, and here as well. And we can also have vector int dp passed. Now we have we have not yet done the memoization. The memoization is nothing but dp of I equals to max of robbed and not robbed. So we are storing this up problem. So hence, if this base case is not reached, we have another case where if the subproblems is already solved, we can just return the solved subproblem, return dp of I. So that's it. So we have done the memoization. So the time complexity here will be an order of n. Since we have done memoization, the space complexity will be an order of n plus an order of n for auxiliary stack space. So we have done the recursion. So recursion, the time complexity is exponential. Exponential is enough. And we have done the memoization technique. Memoization. Here the time complexity was order of n, and the space complexity is order of n plus an order of n, which is auxiliary stack space. Auxiliary stack space. So now let us try to submit the code for this solution. Superb, it gets accepted. Let us also try to optimize the above solution, which is the memoization. We can use a tabulation technique to reduce this order of n auxiliary stack space. So for that, what we can do is we want to initialize everything to be 0 initially, and we can have the base conditions. What is our base condition is nothing but if my dp, if my I have reached the boundary, then I'm just returning 0. It is more than enough, right? So we can run a for loop for int I equal to we have to analyze how the I goes in our recursion. I travels from 0 to n, and in our tabulation it is just opposite. So I should be from n to 0. So what does that mean is I equals to n minus 1, I plus I is greater than or equals to 0, I plus plus, sorry, I minus minus. We can have this recurrence relation, just copy paste this recurrence relation. We can also now we can change this function to be dp of I plus 2, and here it is dp of I plus 1. And my dp of I is nothing but the max of this robbed and robbed. That's it. And here if my n minus 1, even I will be checking if my if there is any dp of I plus 2. So we can have a size initialized dp of n plus 2, therefore we will not have any index out of bound case, or else we can have another if conditions. If I plus 2 is greater than or equal to n, we can just return 0. That is our condition we can include if we are not declaring a size of dp n plus 2. Then finally we are going to return the dp of I as 0, and we can eliminate this function as well. So this is how the this is how the dp tabulation looks like. Now let us try to run the code. Now let us try to run the code. So it gets accepted. So we can also submit our code. Superb, it gets accepted. This is the tabulation technique, tabulation method. We have just converted this memoization technique and tabulation very easily. So the tabulation, the time complexity is order of n, and the space complexity is an order of n, and we have eliminated this auxiliary stack space. So we are not using any extra auxiliary stack space. We are not using recursion here since. So we can see that we are having nums of I and we are having dp of I plus 2 and dp of I plus 1. only these two variables are involved, and such that is nothing but the next and the second next. If we are at this position, let us say we are having 5 6 7. So we are, if we are having this next and we are having the second next, we will be calculating this current value. Consider we are this is the current value. If we have calculated this current value, and there is something that is for the next iteration, we will be calculating this. So for calculating this, we just need this next and this second next. So what we can do is we can just have two variables and we can do a space optimization as well. So what we can do is we can have a next that is initially 0, and we can also have a second next that is initialized with 0. So now we can replace this with next and the second next. Sorry, dp of I plus 2 is nothing but the second next, and this dp of I plus 1 is nothing but the next. And we have calculated this dp of I is nothing but this current value. And if we are having this current next and the second next, then the second next will become second next will be the next, and my next will be the current value for my next iteration. So obviously at the end of the day we can return the next. So that is going to be our answer. Now let us try to run our code and check whether it gets accepted. Superb, it gets accepted too. Even this is kind of a Fibonacci series. Hope you understand what I'm doing here. We are having a previous and second previous in our Fibonacci series, the similar stuff, but only difference is we are adding a nums of I to this dropped value. So with this is nothing but the space optimization technique, space optimization approach. Here the time complexity is order of n and the space complexity is order of 1. Now let us try to submit our code. Great, it gets accepted, and this is a much optimized solution that we can give up in our interview for this problem. So hope you like this problem and like this different solutions. Let us see in tomorrow's lead code daily challenge. Until then, bye.